So let's take a look at an RL series circuit. So a 10 ohm resistor is connected in series with an inductor of 0.01 henries, and that's powered by an AC voltage source of 100 volts at 50 Hertz. It's asking us to draw the voltage phases and to calculate the complex power. So first things first, we'll draw the circuit diagram. I always like to draw the circuit diagram, it just keeps me right. Even if it is a simple series circuit like this. Okay, and what we've got R, and we've got L, and we've got a voltage supply, we've got Vs, and that's 100, and we'll take that as our reference, so we'll have that at 0, and that's at 50 Hertz. R is 10 ohms, and we've got L is 0.01 henries. Alright, so what we should do is calculate the total impedance first of all, because what we want is supply current. And supply current is calculated by the supply voltage divided by the overall impedance of the circuit. So we need this overall impedance, and for an RL circuit the impedance is equal to the resistance plus the impedance of the inductor, which is JXL. We know JXL is equal to 2 pi F times the inductance, so we can just go ahead and do this. So that's 10 ohms, and that's plus J, and we'll just go ahead and we'll just put that in brackets already. 2 pi times the 50 Hertz and L, which is 0.01 henries. And what we get, if we use our trusty calculator, we can just go ahead and directly put it in. So it's 2 pi times 50 Hertz, well, 50 not 5, 50 times 0.01, and that's I. We're using I instead of J, and that's 10 plus 3.14 J. We can convert that into polar, so if you convert that into polar, however you do it, I tend to just use this calculator, and we get 10.48, and that's at an angle of 17.44. And that's ohms. Alright, so we got the impedance. Now what we need is the supply current. So IS is equal to the voltage. So the voltage was 100, and that was at 0 degrees, and that's going to be divided by 10.48, and that's at 17.44 degrees. So going into our trusty calculator, we can go 100 divided by 10.48, that's 17.44. we'll just go directly into the polar of this. And what we get is 9.54 at an angle of negative 17.44. Degrees. Alright, so we got our current, we got our impedance. What we need to do now is find our voltage drops. So what is the voltage drop across the resistor? Well, VL is equal to the resistance times the supply current, which is 10 ohms times 9.54 at an angle of minus 17.44 degrees. So multiply that by 10, convert that into polar, and what we get is 95.4 and that's at the same phase as the current. So the voltage over the, that's a VL, that's meant to be VR. The voltage across the resistor is in phase with the supply current. That's in volts. So let's go and calculate the voltage drop across the inductor. So VL is equal to the impedance of the inductor times the supply current. The impedance of the inductor, JXL, this is J 2 pi 50, we got as 3.14 J. So it's 3.14 J times the supply current, 99.54 at minus 17.44. Now remember, J, that denotes a phase shift of 90 degrees. So you can convert this using your calculator if you like, but it's quite straightforward to just convert that to polar. So it's 3.14, 90 degree phase shift, and we're timesing that by 9.54 minus 17.44. So let's do a calculator. So we got 3.14 at a phase shift of 90 degrees. I'm going to times that by the current, which is 9.54 with a phase shift of minus 17.44, and that comes out, we'll convert that directly into polar, and that comes out at 29.95 at 72.56, so 29.95 at an angle of positive 72.56. And that's volts. Alright, so what we have the voltage drop across VL and the voltage drop across the resistor. We've got supply current and the supply voltage. And we can go ahead and draw our argon diagrams and our phases. So I'll do that below here. Draw our axes first of all. So I'm not very good at drawing straight lines on this. Yeah, see, that's rubbish. What was that? 5, 6. It's more or less 70. So I'll just draw it like this for now. So the voltage supply, the supply voltage, that's our reference, and I think I've done that in this colour, haven't I? So we've got Vs. We've also got, so we'll draw the supply current now, and that's at negative 17.44. So I'll draw that in red. So negative 17.44 we'll just say for intents and purposes that's negative 17.44. So that's IS, and that's also in phase with the voltage of the resistor. What colour did I do the resistor? Blue. So we'll say that's in phase. That's VR. And what we should get a 90-degree angle between the supply current and the voltage of the resistor and the inductor voltage. So we'll say that's wow. And that's VL. So that's the real axis, that's the imaginary axis. So what we've got is a 90-degree angle between VL and VR. And what we also have is we have theta I. What we can do is we can calculate phi, the impedance angle, which we already have, but we'll just do this so it's clear. So that's the voltage minus the phase of the current. So it's the phase of the voltage minus the phase of the current. Phase of the voltage, 0. And we're taking away the phase of the current, which is minus 17.44. And that's positive 17.44 degrees. And we call that the impedance angle actually, because when we calculate the total impedance, that is the angle there, positive 17.44. So there we go. So going back to our triangles now, so if we go to our complex power, what we want is to find S. Yeah, I'll tell you what, I'll do it with this colour for now. So S is kind of like this. So these are connected. And S is equal to VI conjugate. So the complex power S, that's equal to the voltage times the complex conjugate of current. So we got 100 volts at 0 degrees times 9.54 at positive 17.44. So here's why we take the complex, just to reiterate that. The angle of the current is negative 17.44, but the impedance angle, which is what we want, is the positive of that, so it's the, you times in that by -1. What we end up with, so we've got 100 times 9.54 at an angle of 17.44 and that there is 910.14 plus 285.92 J. We convert that to polar. What we get is 954, and there's the angle, 17.44. So 954. So the magnitude's 954 at an angle of 17.44 degrees. And if you're a bit switched on, you'll notice here that this is P, and this is Q. Because that's equal to P plus JQ. So we have our active and reactive power there. So we could say P is equal to 910.14 watts. The reactive is 285.92 volt ampere reactive, and S is a combination of those both. So the magnitude of S is 954, angle of 17.44 VA.